Ever since I started playing around with making SNES music, I was always intrigued by the fur filter in the echo section of the SNES's audio hardware. Unless you have experience in digital signal processing, figuring out what values to use for each of the fur registers was a total black box. Most of the games in the SNES library make very simple use of this aspect of the audio hardware, mostly using it for a standard echo sound, so there weren't many examples on more advanced usage. Recently I learned a bit about digital signal processing, or DSP, for another project, and I realized I could apply that knowledge to build a tool that makes it easy to design certain types of effects using the integrated fur filter. These are effects like low pass, band pass, and high pass filtering. Doing these types of effects in real time on the audio hardware enables doing things with audio that were previously impractical or impossible to do on the SNES. This video is composed of two parts. First, I will go over the theory underlying the tool I made that makes it easy to design fur filters using the SNES's audio hardware. Then I will go over how to use the tool itself. So let's get started. This section is a broad overview of the mathematical concepts underlying the Echo Designer tool. It's not at all necessary to understand every detail. My goal here is just to familiarize you with the graphs that you'll be using in the tool. My other goal is to entertain you. So sit back, relax, and enjoy the ride. So what is a fur filter? Well, first, let's talk about what a filter is. In the context of DSP, a filter is a process that converts an input digital signal into an output digital signal. Mathematically, you can model these signals as infinite sequences of numbers, and you can then model a filter as an operation that converts arbitrary input sequences to output sequences. We often denote the input sequence by x of n and the output sequence by y of n. There are many classes of digital filters with different key properties. We are, however, only concerned with causal fur filters because that is what the SNES's hardware implements. This is the standard model of a causal fur filter. X of n represents the input signal. Each box represents a signal delay by 1 unit of time. Each triangle represents a multiplication by a fixed value. Each circle represents the addition of two signals. And y of n represents the output signal. The addition and multiplication blocks act instantaneously, but the delay blocks work a little differently. On every new sample, the delay block outputs the last value that was on its input. The effect is that a sample value migrates from the left to the right. The nice thing about this model of the causal fur filter is that it's easy to convert it into a precise equation that relates the input signal to the output signal. All implementations of causal fur filters must be representable by an equation in this form. The only thing that differs between different causal fur filters is the set of b values used in this equation. In other words, these b values fully determine the behavior of the filter. These are exactly the values that the SNES audio hardware allows you to control. This equation helps us to implement a causal fur filter, but it's not really clear what effect the filter will have on input signals. To get a better understanding of how this equation affects the input signal, we use a tool called the Z-transform. The Z-transform converts the filter's equation into a form that tells us how the filter modifies the frequency spectrum of the input signal. Before we get into a deeper discussion of the Z-transform, we need to understand what the frequency spectrum of a signal is. Have you ever heard how what we perceive as white light is actually the sum total of the entire color spectrum? The same phenomenon applies to audio signals as well. Every audio signal can be broken up into a sum of pure tones of increasing frequency. The breakdown of pure tones that make up a specific signal is called its frequency spectrum, and each pure tone is called a frequency component of the spectrum. Understanding how a filter affects the frequency spectrum of the input signal enables us to design equalization filters. You may have seen these types of filters on old audio equipment. These types of filters selectively boost or suppress the bass, mids, or treble ranges of the frequency spectrum. The Z-transform is the tool we use to understand how filters modify the frequency spectrum of their input signals. By applying the Z-transform to the fur filter, we'll be able to see the relationship between the B values and the filter's effect on the frequency spectrum. This will make it much easier to decide which B values to use when designing a FIR filter. H of Z is called the transfer function of the filter. The transfer function describes how the input frequency spectrum is modified by the filter. Before we try to understand how the transfer function works, we should first understand what Z represents. For the purposes of this video, it's enough to say that Z can be any two-dimensional number in the complex plane. For audio signals, however, the only Z values in the complex plane that matter to us are the ones along the unit circle. Let's stop here. The angle of the Z value along the unit circle corresponds to a frequency component in our input frequency spectrum. In this case, that angle is 45 degrees. To convert that to a frequency, we divide by 360 and then multiply by our sample rate. If our system is running at a sample rate of 32 kHz, this Z value corresponds to the frequency component at 4 kHz. The output of the transfer function is also a two-dimensional number in the complex plane, but it has a different meaning than the input Z value. Let's consider the example transfer function below. Here we are tracing the output of the transfer function as we move the Z values along the unit circle. Let's again stop at the point where the Z value is at 45 degrees, or in other words, the 4 kHz frequency component of our input signal. On the plot to the right, you'll see a single cycle of the 4 kHz input frequency component. Remember, this is a pure tone and you'd expect it to sound like this. At this Z value, the angle of the transfer function output is 276.9 degrees. This angle is exactly the amount of phase shift that our filter applies to the 4 kHz frequency component. In other words, if we pump in a 4 kHz pure tone into our filter, that same pure tone will come out of our filter, except it will lead the original signal by 276.9 degrees. The magnitude of the transfer function output at this Z value is 1.15. The magnitude tells us how much the filter attenuates or amplifies the corresponding input frequency component. Continuing with our example, if we pump in a 4 kHz pure tone into our filter, that same pure tone will come out of our filter, but with a magnitude that is 1.15 times the magnitude of our input pure tone. By evaluating the transfer function at every Z value along the unit circle, we can determine how the filter modifies the phase and magnitude for the entire frequency spectrum of our input signal. Under normal working circumstances, we don't use the complex plane to visualize the transfer function of the filter. Instead, we use separate magnitude and phase plots. In the magnitude plot, the x-axis corresponds to the input frequency, and the y-axis corresponds to the magnitude of the transfer function output. In the phase plot, the x-axis corresponds to the input frequency, and the y-axis corresponds to the phase of the transfer function output. Going back to our example, at an input frequency of 4 kHz, we can easily look up the corresponding magnitude and phase effect of the filter. If you've made it this far, congrats! There is just one more tool that you should learn to effectively design filters at the Z-transform level. Let's again consider our example transfer function h of z. What if I wanted to know what Z values result in a transfer function output of 0? In this case, we can do basic algebra to get that h of z is 0 when z equals 1 plus or minus the square root of 3. Now let's plot these two Z values on the complex plane along with the unit circle that corresponds to our frequency spectrum. This is called a pole zero plot. The circles in the pole zero plot represent the Z values in the complex plane where the transfer function output is 0. We call those Z values zeros. Usually though, this plot is given without the labels on the zeros. It would also show the poles of the transfer function, but those aren't necessary for us. The pole zero plot is useful for us because as a general rule of thumb, the closer a Z value is to a 0, the more the output of the transfer function at that Z value will be attenuated. Let's bring in the magnitude plot to see that a bit better. You can see that as we move along the frequency spectrum, the closer we get to the filter's zeros, the lower the magnitude response of the filter becomes. Conversely, as we move further away from the filter zeros, the magnitude response of the filter increases. Earlier, we found the zeros of our example transfer function by setting it to 0 and solving for z. One way to think about that process is that we converted the transfer function into its corresponding zeros. The algebra actually works both ways, and we can just as easily convert a set of zeros into its corresponding transfer function. This property allows us to design equalization filters by first choosing where the zeros will be in the pole zero plot and then converting the zeros into the corresponding transfer function. Designing the filter in this way is intuitive because we know that wherever we place a zero, the parts of the frequency spectrum that are close to that zero will be attenuated. For instance, if we want lower frequencies to be attenuated, we place our zeros near the part of the unit circle that corresponds to lower frequencies. This idea is the essence of the Echo Designer tool. That was a lot of material in a short period of time, so let's recap everything we've gone over. First, we introduced the concept of a filter as an operation that maps input sequences of numbers to output sequences of numbers. Then we went over the structure of the FIR filter, how to express it as an equation, and how it's fully defined by the b values used in that equation. Then we discussed the z-transform, how we can use it to get the transfer function of the FIR filter, and how the transfer function shows us how the filter modifies the frequency spectrum of the input signal. Last, we talked about how we can design filters by first selecting the zeros that we want our transfer function to have, and then deriving the b values of the FIR filter from there. Now we're ready to try out the web app. Okay, so now that we have an idea of what's going on behind the scenes, here we are at the Echo Designer tool of the SuperMediaPAK web app. You can see the FIR values from 0 to 7 here. These are the b values of the filter. This is the pole zero plot as we talked about. Here's the magnitude response plot, and here's the group delay. The group delay is sort of like a stand-in for the phase response. We're not going to talk about that too much here, so just ignore it for now. And so you can see as we change the FIR values or the b values of the filter, the tool will automatically show us the zeros that correspond to those b values. So you can see all the zeros here. And the nice thing about the tool is that, we can design a filter by trial and error, moving around these FIR values. And you can see the effect on the magnitude response in real time. But like I said, it's not really clear how we get a magnitude response. There's no real systematic way of getting a magnitude response we want just for manipulating the FIR values. It's much easier to move around the zeros of the filter to get a response that we want. So what I've done here is I moved the zeros all to the high frequency components of the frequency spectrum. And that was very simple. That was just very intuitive for me to do. And we can look at the magnitude response, and what we'll see is that the higher frequency components have been attenuated. The maximum amplification here is negative 30 decibels, whereas the lower frequency components of the frequency spectrum, they all have a relatively higher magnitude. And so that's the beauty of this tool. It allows you to interactively build a filter by just manipulating the zeros. Now, this tool also has a bandpass filter generator. And so the nice thing about this is that when you're let's say you're playing live and you want to modulate the filter live, it's tedious to even, work with these zeros. Although you can, maybe that might be something cool that you want to do. But most of the time it's tedious to, move these zeros around. Let's say you want to go exactly from one spot to another, and that you already know how you want the response to look like. It's tedious to say, okay, I have to move the zero here, move the zero here, and all that. Likewise, it's even more tedious to move these FIR values around too. And so the bandpass filter is basically a filter that allows frequencies in a certain space of the frequency spectrum through, and it attenuates or rejects all the other frequencies. So the frequencies that it lets through are usually centered around the center frequency. And the filter width defines how many frequencies from that center frequency are let through. So for instance, let's say we pick a center frequency of 8,000 and we set a filter width of 2,000. You can see that basically at 2,000 hertz above 8,000 is 10 kilohertz. We have an attenuation of negative 2 decibels, and the same for 6,000, which is 8,000 minus 2,000. We also have an attenuation of negative 2 decibels. And so as we increase the filter width, you can see that the attenuation decreases the wider we go from the center point, which is 8,000. And so I'll show how that sounds here. So as we decrease the filter width, we're basically letting in a narrower range of frequencies through. And so this bandpass filter generator is nice because it allows us to generate filters on the fly only using 2 parameters. And this allows a very common effect called like a filter sweep. So I'll show you guys how that sounds. So the filter sweep, basically, you pick a very narrow filter width, and then you just sweep the frequency spectrum, changing the center frequency. So I'll show you guys how that sounds here. So that's a very common effect. You've probably heard it many times in many different tracks. Instead of changing the center frequency, you can also change the filter width. So if my center frequency is at 0, I can modulate my filter width like this. And so as the filter width goes to 16 kilohertz, that basically has no effect on the sound at all. And so you can see at 16 kilohertz, the magnitude response is flat, and it's at 0 decibels, meaning that it doesn't change the input sound at all. And that's because the entire frequency spectrum of the SNES is from 0 to 16 kilohertz. And so that's cool. You can basically generate this filter sweep, live. So the last feature I want to go over is the echo feedback. And so what the echo feedback does is that when it's set to a value that's non-zero, you actually start to get poles in this pole zero plot. And so what do the poles mean? Well, the poles are kind of like the opposite of the zeros. Wherever the zeros are, remember we said that the frequency components that are near to the zero will be attenuated. Well, the poles do the opposite. All the frequency components that are near the poles are amplified. So you can see that as we increase the magnitude of the echo feedback, you can see this pole is getting closer and closer to the lower frequencies here. And so what you would expect is that when I play the sample sound, I'm going to get even more of a sort of amplification of the lower frequencies than I would without the feedback. So this is how that sounds. So that's with no feedback. And so I'm going to increase the feedback again. And so you can see that's really all due to this pole. And so because of the way the SNES hardware is structured, we can't control the poles in the same way that we can kind of manipulate the zeros. These poles, the shape of these poles is more or less dictated by the shape of the zeros. All we can really do is modulate basically how far the poles are from the origin of the pole zero plot. And so the nice thing about the Echo Designer tool in the web app is that it at least shows you where these poles are going to be. And that'll give you an idea of how the feedback will modulate the magnitude response of the filter. So the other setting we have here is the echo delay. And the echo delay is very intimately tied to the feedback value. When the feedback is 0, delay has no effect. But when feedback is not 0, the delay, you can see that the delay causes the magnitude response to get very spiky. And the reason that is that the echo delay basically causes a ton of poles to appear, and they're all scattered around the frequency spectrum of the pole zero plot, the unit circle. And there are very, very many of them with only, even when the delay is like a small value, there are more than 500. And so the effect of this is that when there's very many poles near the unit circle, you can see that the magnitude response gets very spiky. And it gets spiky wherever there's a pole, because remember, the poles cause the magnitude response to increase. And so the sound that you get when you have a feedback and a delay is you kind of get this like robotic type sound. Here, I'll show you.
Why do I dream silly dreams? Why do I dream silly dreams? Why do I dream silly dreams? Why do I dream silly dreams?
So you get this sort of robotic sound, and you may have heard this sound in other tracks. I think Daft Punk uses this effect, and many other people use this effect because it's not even related to the FIR filter. I can set my FIR filter to nothing, so the FIR filter is just passing through values normally. So that's just the sound pass through without any alteration. And so if I set my echo feedback and I have a delay.
Why do I dream silly dreams? Why do I dream silly dreams?
And so that's a very common effect. It's heard often. It's very easy to implement, so that's why I hear it so many times.
Why do I dream silly dreams?
And so with that, that's the new Echo Designer tool in the Super MIDI Pack web app. I had a lot of fun using it, making this video, playing with sounds, trying to craft the demo. And it's kind of cool, you know, in real time, messing with the filter response and seeing what you can get. So, you know, if you have a Super MIDI Pack, have fun with it, try messing around with it, and see if you can create something cool. And so we'll close this video with the full demo. And if you guys have any questions, leave them in the comments, and I'll see you later. Bye-bye.
Why do I dream silly? 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 Why do what